Good afternoon. Welcome to the Filitalia Symposium on Innovation in Aerospace, Present and Future. A coloro che sono collegati con noi dall'Italia, buon pomeriggio e benvenuti al simposio di Filitalia su innovazione in aerospazio, presente e futuro. My name is Antonio Paesano, and I have the privilege to host this symposium that is promoted by the Italian Consulate in Philadelphia and the Italian government, which we greatly thank. The symposium is also organized by Filitalia International, a prestigious Italian-American non-profit organization founded in 1987 to promote and preserve the Italian culture, heritage, language, and history throughout the world. I also like to acknowledge the IT firm Hyperdesign for handling the present connection, social media, and other IT aspects of this symposium. Today, we are very lucky to have 5 speakers from companies and the university that are leaders in aerospace. We will hear from them about the progress done in technologies for aerospace and the expectations for the near future. I greatly thank today's prestigious speakers for their time and sharing their knowledge. So to our audience today, I say fasten your seatbelt and enjoy your flight through aerospace technology. Before we dive into the presentations, let me introduce Dottoressa Patrizia Calanchini Monti. She's the director of the Educational Office of the Consulate General of Italy in Philadelphia. Please, Dottoressa.
Good morning, thank you. I'm very pleased to represent the Italian Consulate in Philadelphia and to extend the greetings and best wishes of our Consul General of Italy, Pier Forlano, and also to inform you that today's symposium has been officially included in the catalogue of events of the International Day of the Italian Scientific Research. I would like to say that we really appreciate your efforts to portray Italy not only as a country rich in cultural and artistic heritage, but also as a leader in scientific and technological developments. It is great for us to have events within the Ciao Philadelphia program dealing with scientific events, as well as with topics dealing with sustainability, which is one of the main challenges worldwide at the moment and in our country as well. On behalf of the Consulate General of Italy in Philadelphia, I would like to thank Filitalia International for the fruitful cooperation with the Consulate, and also to draw the attention of today's participants to all the other events of the Ciao Philadelphia catalog, which ranges from literature to design, from cinema studies to scientific research. And I very warmly encourage you to look them up in the Ciao Philadelphia website, as it provides a really rich offer of interesting opportunities to debate about a wide range of topics, always keeping Italy and the Italian American community at the center. I'm also pleased to remind you that in 2021, we are celebrating the 160th anniversary of the diplomatic relationship between Italy and the United States, which represent again a further opportunity to emphasize the positive cooperation between our two countries. Thank you very much, and buon lavoro.
Thank you, Dottoressa. And now it's my pleasure to introduce Dr. Pasquale Nestico. He's professor of medicine at Jefferson University and is the founder and president emeritus of Filitalia International. Please, Dr. Nestico.
Can you hear me?
Yes, we can.
Excellent. Thank you, Dottoressa Colanchini Monti. Thank you, General Counsel Forlano, and friend of my personal friend and friend of Filitalia International. Thank you, Antonio, for your brilliant career, as well as your dedication to the mission of Filitalia International. And I bring to you also I saluti. Welcome from our esteemed President, Paola Bonavitacola, and hello to all the speakers of incredible talent. And I am certain that will personally enjoy the presentation. I'm in the midst of patients. You can tell the way I'm dressed. And Filitalia International has 33 years of experience of the third sector. It's 99.99% volunteer. And our mission is language and culture and services to others. Our motto, M-O-T-T-O, is humility, justice, and honesty. We have a beautiful center with a history of Italian Immigration Museum, housed by our center. Please come to Philadelphia. We'll treat you nicely, and we'll show you the city, how beautiful Philadelphia city is. We have 22 sites between Italy and the United States. We're also looking to expand in South America. We have an incredible team. Congratulations for today, and we really, really thank you for your presentation ahead of time.
Thank you, Dr. Nestico. Let me introduce now the first speaker today, Mr. Todd Hammer. Very brief introduction because of the little time we have today. Mr. Todd Hammer is currently founding president and CEO of Belotti America, a subsidiary of Belotti Italy. A world leader in the design and manufacture of 5-axis machine tools for aerospace, automotive, nautical, and plastics sector. Mr. Hammer works with market leaders such as Boeing, General Atomics, Lockheed Martin, Northrop Grumman, SpaceX, Tesla, and their supply chains. He's also been the director of SEMPI Texas chapter and co-general chair of SEMPI. Please, Mr. Hammer.
There we go. Okay, I'm on the wrong slide. Pardon me just a second.
That proves we are live.
Exactly. Okay, here we go. All right, thank you very much. It's my pleasure to participate in this event. I've proudly represented Italy for decades in the machine tool business, and my presentation is just a quick talk on present and future, but I think it's also important to mention just a little bit of the past and how aerospace ties into automotive going forward. For those participants that CNC or NC is not a familiar term. NC is numerical controlled and dates back to the 1940s, back when punch cards and punch tapes were used by a company called Parsons Corporation in Traverse City, Michigan, to start to make helicopter blades using digital input. Fast forward to 1977, and Bilotti Spa was formed in Suicio, which is a small village just outside of Bergamo. In the aerospace industry, we generally see one of two types of machines used, either 3 axes or 5 axes. X and Y indicate the length and width of the machine, and Z the vertical. More often, we see 5 axes, which adds a C axis, which rotates around the vertical, and an A axis, or sometimes referred to B axis, which swivels around the C axis. So here you see a typical 3-axis application where all of the machining is perpendicular to the face of the part. And here you see a couple typical 5-axis applications where you're shaping a contour, or in this case, trimming and drilling. Here's a little closer view of these 5 axes and an example of a typical head, a 5-axis head. Here's your Z-axis, your X-axis, Y-axis, and turning of this head for C and swiveling of this spindle. What's important is, even though an aerospace part, in this case aircraft, may be very thin and appear flat, because of the makeup of the composites, it's still necessary to mill this with 5 axes in order to have the cutting tool perpendicular to the composite material. Here's a typical application in aerospace where it's difficult to see here, but we've got a machine that has 2 gantries. One gantry has a 5-axis milling head here, and on the other gantry, which is closer to the viewer, a 5-axis abrasive water jet head. So in this technology, we would use the abrasive water jet head to rough out the geometry of this part, and then come behind it and do a final trim and possibly some milling of pockets or drilling of holes. Nowadays, if you've flown on a A350 from Airbus or a 787 from Boeing, you'll see that there's a lot of talk about composites, but yet there's still a tremendous amount of aluminum used in the industry. It's really a daily contest on aluminum industry trying to take business away from composites, and composites trying to drive down the cost of the composite components to be competitive with aluminum. Here you see the Boeing 787 Dreamliner, which as you can see, I apologize for the poor image, but by weight, it's an impressive 50% of the weight of the aircraft is made up of composites of one kind or another, with aluminum and titanium still holding a strong percentage of that. For those from Italy and Europe, you'll be very familiar with this slide showing the new generation of spacecraft, and what all of these have in common with automotive is it's all about lightweighting. Lightweighting equals lower cost, whether that's more freight or passengers in aerospace, better gas mileage in automotive, larger payloads in space, not being detectable by radar in our defense to protect ourselves, or going faster and being safer in motorsports. Here you've got a slide that shows the more satellites that we can stack in the spacecraft, the lower the cost. So the lighter we can make this entire spacecraft, the more satellites, for example, we can load in here and drive that cost down. This is a very much global industry. As you can see from this slide, we have countries around the world that are participating in just this one program. Italy, setting aside the manufacturing of the 787, Italy is a very strong player when it comes to aerospace and automotive, in that a great deal of machinery is manufactured in Italy, is used around the world to machine these parts, either at an OEM, tier 1, 2, 3, and so forth. Nowadays, present and going into the future, machining accuracy is becoming more and more important, because in order to drive down cost, we've got to be able to create assemblies that at the OEM during the original assembly, sure, they're easier to assemble, but more important is out in the field or the depot, they are bolt-on components, very tight tolerance components that bolt on just as easy as say a replacement part for an automotive application at a local auto repair shop. And so we're constantly driving towards finer and finer resolution on our tolerances. Here's an example of just a simple countersink test provided for a composite application, and we're down into the single-digit microns in terms of accuracy for tests like this, which make it quite easy to bolt on, for example, that new canopy for that fighter jet. Here's a little look into the future. Again, if we use what is currently being done in commercial aircraft, defense aircraft, spacecraft, this new urban mobility is going to be very much like the automotive industry, where we need to make them, manufacture them at a much lower cost and have parts that are easily interchangeable. There's a view over our famous city of Paris. Why composites? As you can see from this chart here, steel, which we would all consider to be a very strong material, is at the bottom end in terms of the traditional aluminum and titanium uses, and titanium, being the strongest of those, is only equal to glass fiber composites until you start orienting those fibers in different directions. And then of course carbon fiber becomes on a magnitude of 5 times. In a going forward, we take the very labor intensive carbon fiber parts that are laid up by hand today, and companies around the world are racing towards trying to get these parts manufactured at a much lower cost, but yet still be flyable. So here's an example of an article just from this last week in Composites World, where Airbus is sponsoring the Wing of Tomorrow program here, and a thermoplastic composite rib is being provided as a demonstrator to prove out that reliability of that technology. And thermoplastic composites is really using technology that we would consider to be old technology in automotive to adapt to something that is a very low volume application compared to automotive. I had the privilege last week while I was in Italy to tour one of Persico's facilities just outside of Bergamo. And Persico is another Italian manufacturer that is really active worldwide, like Bellotti, in helping industry drive down cost. And they were kind enough to share a few slides for this presentation today, where they're working on taking technology that is old technology from automotive and forming and cutting in one step in the mold parts that are typical aerospace parts. So here you see a few parts from helicopter applications. And what even though Persico is a customer of Bellotti's, what interests me the most in a going forward perspective is the faster these parts can be produced, the more demand there is on companies like Bellotti to be able to machine the parts more efficiently to try to keep pace with folks like Persico. So the next few slides here will just be some of the small examples that we see helping aerospace in the the coming years. Those tier 2, tier 3 suppliers become more efficient. So the more efficient they become, lower cost, and the closer we can come to that automotive, let's say, pace. So here's a simple example of a device that in the machine tool industry is very common, but in composites machining, not so common. What this does is give you the ability to introduce a fixture, reintroduce a fixture to a machine tool and have it repeatable, virtually perfect, within microns. And here's an example of a customer that is a tier 3 supplier to an aircraft manufacturer. And we heard that this was a purpose-built, let's say, specified machine that incorporates a real short part on a 0-point tool that allows, as you see in the lower right-hand corner, a longer part. And so within a minute or two, you can change over from trimming and drilling a very short part to something that's longer. And of course, the configuration can be, anything the application requires. So here's a little closer view of the type of part that is being machined in that machine. And here's an application where carbon fiber is being machined wet as opposed to dry. Another example, here you see a machine that's 23 meters long and 7.2 meters wide and has a z-axis of 4.5 meters. We can divide this down the middle or divide it across the center and be able to load and unload on one end while we're machining on the other end. Again, it all in the objective being to keep the machine running constantly, as opposed to these long periods of time down machine while we're unloading or reloading a part or a fixture or both. Here's a smaller example of that where we'll introduce shuttle tables where we can be machining inside the machine here on one table while we're unloading or reloading, maybe exchanging the fixture on another table, and then these will alternate back and forth. Here's an example of taking that one step further, where we've got a machine tool that has 2 spindles, 2 5-axis heads that can be machining 2 different type of parts in a machine while the operator is out on the outside of the machine unloading or reloading. At the end of this cycle, this table rotates 180 degrees and introduces the 2 tools that you see in the foreground and exchange those for the ones in the background or inside the machine envelope. Here's one of the earlier slides illustrating just the divider here that we've got that allow us to unload, reload at one end while we're machining on the other end. If we look at these raised pods here, you notice that these are fixed in the floor. Something in a going forward, so the future is that we're starting to drive these rows in and out of the machine, drive these electronically back and forth to suit the part. So here you see the machine illustrated from the end of the machine. The purpose here is there's applications where you may want to have an installation where you've got a typical cast iron T-slot table and have all of these universal fixtures outside of the machine. And then let's say on this afternoon or tomorrow, you've got an application similar to those that I showed earlier, and you want to drive some of these or all of these into the machine over that cast iron T-slot table to create a very flexible machine tool. Here's a view of that machine from the side, showing one of these driven down to the other end of the machine, a couple of them in the machine, and the rest still stacked outside of the machine. We've got a speaker a little later on that'll go into a great deal of detail on 3D printing or additive manufacturing. Belati has partnered with a company in the Netherlands by the name of Seed to create a trade name Bead, where we'll take Seed's additive technology and install that in our large machines. So we'll have applications, for example, here where we'll print very large tools for nautical and aerospace industry, whether those are plugs, molds, tools for autoclave curing. And we really look forward to bringing that to this aerospace market. Here's a quick shot of a rendering of what that'll look like. Seed here is their contact information if you want to look into that. Here's our mothership contact information. A few details on them and my contact information. My colleagues in Italy, their contact information as well. And it's been a pleasure presenting, and I look forward to any questions that may be present, or if somebody has something that they'd like to ask that's confidential, feel free to email me or telephone me. Thank you, Antonio. Antonio, you're on mute.
Thank you, Mr. Hammer. It was interesting. Interesting the adjustment that, I mean, the fact that your company is trying to use established technologies in new applications or new ways. I have a question for you, although it's about 3D printing. So the question is, how does improvements and expansion in 3D printing technology impact your business model, if at all? and how are you adapting to this technology? If you're gonna have a brief answer, a couple of minutes. Thank you.
Yeah, so if I could answer it this way, Antonio, what really interests us about 3D printing is there are a lot of applications where we feel our typical customer has a need to print a large tool of some kind, and that printing is going to be much more efficient, again driving costs down, and so we see it as a very interesting technology to drive their costs down, and we feel it's something that I shouldn't say it's rocket science, but it's something that we feel very complementary to our existing technology. So it's really about helping the customer become more cost effective, more competitive.
Okay, thank you, Mr. Hammer. Appreciate your time. Appreciate your information. I like to move now to the next speaker, Mr. William Sunic Jr. is the head of, he works for Leonardo Helicopters and Augusta Westland in Philadelphia. And he's the head of Tilt Rotor Marketing. And is responsible for the development of marketing and business strategies for his, and prior to joining Leonardo Helicopters, Mr. Sunic held numerous leadership positions at the Boeing company within strategy, marketing, sales, market development, and engineering. He was also a member of the presidential helicopter team while he was at Sikorsky Aircrafts in 1992. Please, Mr. Sunic.
Thank you, Antonio. I am going to share my screen here. Okay, hopefully that's working. And let me start. Wonderful. Okay.
I can see it.
Okay, let's go to presentation mode. Okay, outstanding. Hopefully you can see just the slide now. Is that correct?
That's good.
Wonderful, wonderful, great. Thank you so much. It's my pleasure to be with you here today to share with you perspectives on innovation within aerospace. As head of tilt rotor marketing for Leonardo Helicopters, I'm excited to share with you several innovative technologies we are working on today and for the future. A little background here about Leonardo. Approximately 50,000 employees worldwide, headquartered in Italy, in Rome, but spanning the full spectrum of aerospace and defense solutions across multiple domains, air, land, sea, space, cyberspace, and unmanned. And the common denominator, I'd say, is a full breadth of customer support services and training options across all those products and systems. Now, to go in a little more detail, as I mentioned before, I'm a member of the air domain, a helicopters unit, and to take a little closer investigation with that, I'd like to share with you the product portfolio within Leonardo Helicopters, and this was Heritage Augusta and Westland Helicopters in the UK. And you see our portfolio there, and it's bounded by two horizontal bands, one in blue, denoting the civil or commercial helicopter rotorcraft lineup, and another denoted in green filter, indicating the military or government use platforms. So you'll see extensive product range across all weight categories. And predominantly, we have dual use platforms. as we say, civil as possible, but military where necessary. So inherent in those designs are both civil and military applications. And I like to point out and start with one aircraft in particular and share with you this family concept of innovation that we're currently utilizing. And that starts in an intermediate class, the AW139, there in the blue, and then repeated also capabilities in the green. But ironically, 20 years ago, this past February, we had the first flight of that aircraft. And over the 20 years, that has evolved and is now the best-selling intermediate twin-engine helicopter across the world. In fact, we've recently delivered our 1,000th aircraft. But starting with that design and that philosophy here, we expanded that across our product range to a larger twin engine, a medium or super medium, as some would say, the AW189, and then a smaller, a light intermediate twin engine helicopter, the AW169. But sharing that same AW139 design philosophy, certification, and standards, or DNA, as we say. And what that equates to in terms of operator innovation is a 20% commonality of parts across all three of those airframes, a 30% commonality in maintenance tools and ground support equipment, and 40% reduction in overall training time for maintainers and air crew. So a lot of investigation goes into the acquisition costs of an aircraft, which is a very large component of cost. But when you're employing aircraft over a number of years or decades, going out 20 or 30 years, the acquisition cost is actually a very, very small component of the overall cost. And really, it's the logistics tail or the life cycle cost of that aircraft, the parts, the tools, maintaining tools, the ground support equipment, and then the training for the multiple air crews and maintainers that will be part of that aircraft through its lifetimes. That is the biggest cost driver. So having those savings and those synergies across those three aircraft, that family concept, that's operational efficiency. That's real world innovation for our operators. And that's tangible results that they can benefit to today that we're really, really proud of. Now, going forward from that, I'd like to share with you a new aircraft we're developing. In fact, it's a new class of aircraft, the AW609 tilt rotor. You'll notice in the photo there on the slide, it harnesses tilt rotor technology. It has twin nacelles with twin engines that enables it to take off vertically and fly very similar to a helicopter. However, those nacelles rotate, and they'll rotate 90 degrees down, and enables it to fly like a fixed-wing twin turboprop airplane. And what that does, it enables the best of both worlds, really. It enables the runway independence of a helicopter that you can just about take off anywhere, or have the capability of vertical maneuver during your flight, mid-mission hover, things like that. With the excellent and higher speeds, longer ranges, and higher altitudes afforded by turboprop airplanes over helicopters. So you really have the best of both worlds in that tilt rotor technology. That's one technology, but now adding to that, composites, and Todd did a great job, enjoyed his presentation talking about composite technology, which began on the military side, and we see it going on to the commercial side in airliners, and now we're starting to see it in rotorcraft, first again on the military side, but now on the commercial side. So the AW609 takes full advantage of that and has principal structures made of composites. And then even going a step further, our airframe, the cabin section, is pressurized, which is unheard of in any rotorcraft. Helicopters fly lower. They're bounded to about 10 1,000 feet operationally. Some, go a little higher, but then you need some supplemental oxygen, things like that. But for a commercial helicopter, 10,000 feet is about the limit. But having a pressurized cabin, as the AW609 does, enables you to fully exploit the twin turboprop light cruise mode to fly at higher altitudes of between 20 and 25,000 feet. So what that enables is you to fly over obstacles like mountain ranges, whereas a traditional helicopter would have to take a more circuitous routing through the valleys or whatnot, or even an obstacle like a bad weather system, out there 15 or 20,000 feet, that you can literally fly over that and enjoy direct routing instead of a longer, more circuitous routing. Also at airspeed, you're flying in the smoother air, and you have higher airspeed advantages due to that altitude here. Now, in the unlikely event that you are at a higher condition and you have icing, we have a full ice protection system employed in the aircraft to enable flight into known icing conditions. So to really exploit that altitude advantage there. And then finally, a fly-by-wire flight control system. So in old days, we used to have mechanical linkages going from the pilot's control sticks into the control surface here. But we have multiple helicopter-like control surfaces and fixed-wing airplane-like control surfaces. Now, in the cockpit, the pilot would be very familiar from a helicopter perspective to our inputs. We have a center stick, rudder pedals for the feet, and then what a traditional helicopter pilot would call a collective lever we have, but it's a power control lever because in airplane mode, obviously it behaves more similar to a throttle. But having a computer in the loop there, we're able to take the pilot's inputs and translate those into the desired control system, control actuation to get that desired effect that the pilot wants to command. They don't have to worry about where they are within the flight regime if they're flying as a helicopter within the nacelles vertically or down as a twin turboprop airplane with the nacelles oriented at 0 degrees. The flight control fly-by-wire computer system figures all that out, and the pilot continues to input via the traditional helicopter-like controls. But it's truly the summation of those 5 technologies: tilt rotor technology, composite pressurized airframe, fly-by-wire flight control system, and a full ice protection system that makes the AW609 one of a kind. No other aircraft on the planet has a summation of those 5 technologies here. And I would make a comparison to the iPhone. When the iPhone was introduced, it wasn't the first phone to have an internet browser. There were other devices that had those out there. What it did was take those technologies and employ them in a user-friendly, in a more manageable and usable package. And that's what we believe we have here. These technologies have been out there. We are the only ones to combine all 5 of those in one platform that we are really excited about the benefits that we can offer to our customers across multiple mission sets that we'll think they will see tremendous operational synergies here. And talk a little bit more about those capabilities here, of having the runway independence, the vertical maneuver of a helicopter with speed, the higher speeds, longer ranges, and greater altitudes of a twin turboprop aircraft here. A lot of it comes down to time. Now, in the US, a popular saying is time is money here. And where we're located, Philadelphia, is arguably one of the most, it's kind of in the middle of one of the most traveled routes between two of the capitals within the United States, the center of government, Washington, D.C., and then the center of business and commerce, New York City and Wall Street here. That is, at best on a high-speed train, a 2.5-hour trip from Manhattan directly to downtown Washington, D.C. There are airplane services you can take to fly from New York City to Washington, D.C. However, they're a bit outside the city centers. They're not off Wall Street, right? They're a little further out, and they don't land you in downtown Washington, D.C. So though it's an hour, you're going to have surface transit to and from your original point of origin and then your final destination here. But to have the point-to-point capability of the AW609 to take off vertically from Wall Street and then to fly in an hour land directly downtown Washington, D.C., that's a game changer. And so for a business executive that is overbooked in their time and whatnot, to be able to fly down to Washington, D.C. from New York, conduct your business, and then make it back up by lunchtime, that's huge, right? And so time truly is money there. And now I would pivot toward emergency medical services here. And time equates into a different savings here. I've talked to a lot of operators around the world in remote regions that don't have the benefit of hospital density that we enjoy here in the greater Philadelphia area. So they're all at long distances from hospitals and more rural areas that to make a pickup at a point of injury often involves multiple platforms, whether it's a car to drive to a opening or even a helicopter to fly to a regional airport to then take an airplane to travel to a metropolitan airport and then a helicopter or surface transport to the hospital, right? To have the capability to fly directly to the point of injury to that full service metropolitan hospital that has a full capability across all ailments here, that's a game changer. And so that time savings, that can mean the difference between a permanent injury or not, right? And now we even look toward search and rescue. And so traditionally, it's a mixed fleet, what we call it. The search is done by a fixed wing airplane because it has the longer range, has a longer enduring loiter time over the search area that can run a search pattern over to locate and identify those in distress, and then radio the helicopter that has the shorter fuel reserves, but has a vertical maneuver capability to stop in mid-flight and make the pickup and rescue here for those in distress. So a time savings of having a platform that can do both of those jobs as two different platforms in one platform to do a fixed wing type search, you know, locate on scene very, very quickly and have that loiter time to perform a search and then prosecute the rescue with the vertical pickup of a winch hoist of those in distress. And then the added capability of pressurized airframe for some ailments, if it's a deep sea diver with a lung injury or things like that, to have sea level standard pressure available in the airframe, you know, that synergies between fixed wing and rotary wing, that difference and savings in time could be the difference between life and death here. So really a lot of very tangible savings depending on the operator here between those capabilities here that's only afforded today in the AW609. And so, you know, looking at aviation history, it's steeped in improvements in speed and range and altitude. And you'll see here the AW609 is no different compared to other commercial vertical lift platforms out there, your typical helicopters or even compound helicopter technologies that employs auxiliary type propulsion devices. The AW609 does better them in terms of speed, range, and altitude, but even goes a step further in terms of noise or CO2 burned during its flight here by flying more efficiently in using the benefit of a static wing, right, to fly off of that instead of a rotary wing. Here, we're able to get better noise signatures or less CO2 emissions produced. So taking a step back and looking at the entire history of aviation, you know, it's pretty much been the same. We either drive or take a helicopter to an airport, then to hop on a fixed wing airplane to fly to our destination, and then drive to our final point of our journey here. we're really, really excited about offering a new way of flying here, of true point-to-point transportation. And you think, back to the days of Star Trek when you kind of beam from one place to the other. Well, that's kind of the capability that the AW609 can afford here. The vertical independence of a helicopter, speed, range, and altitudes of a fixed-wing airplane to offer true point-to-point transportation. And we think this is an exciting time in aviation, and think it's about time that we demand more capability from our aircraft. So thank you very much, and I'd be happy to entertain any questions you may have.
Thank you, Mr. Sunik. I have a question that requires a quick answer. So in case someone in the audience is interested, what is the price tag of this aircraft, roughly?
So it varies on application. You saw multiple missions there, whether it's utility type, oil, gas, offshore energy, resource development, to search and rescue and EMS, VIP, corporate type. So we're still setting the final price, but typically it'd probably be between $25 and $30 million.
Okay, 25 and 39 between.
25 and 30, 25 and 30.
Okay, 30. Okay. Okay. There is a question, but I'm not sure we have time. Sorry. I am concerned. So, or do you have a? Let me see if you can answer quickly in 1 minute to the question. Does the current infrastructure fully support the capability of this aircraft? If you can answer in 1 minute, please.
Sure. So the AW609 fits on existing helipads. In fact, very similar to our AW189, the large medium I showed you before on our product portfolio, slightly larger than that. If you're familiar with other larger commercial helicopters like the S92 or H225, it actually fits in helipads smaller than that. So those infrastructures are already in place. Now, also, we have the benefit of being a tilt rotor. We can also use airports because it is an excellent short takeoff and landing aircraft, and it gets even better performance by having a little bit of a runway roll.
Okay, thank you very much. Sorry, we don't have time for a second question. Maybe we can check later. I want to say something I forgot to mention, that this event will be later posted on YouTube. Okay, so let's move to the next presenter, Mr. Alessio Lorusso. He's the CEO and founder of Robos, a 3D printing company. He was included in the Forbes 30 Under 30 list 2018 as one of the most talented 30 European managers in the industry category, entrepreneur and visionary in the additive manufacturing field. He won the Entrepreneur of the Year award by Ernst & Young, and when he was only 17, he built his first beltless 3D printer, and in 2015 he founded Robos, doubling its turnover year after year. His goal is to bring value of producing at the point of use in favor of net economic advantages. Please, Mr. Lorusso.
What an introduction, Antonio. You set so high expectations now.
I did not do you a favor, right? So.
Thanks for inviting me. It's a very pleasure to be here today with you. So I'll share my screen. Could you please confirm that you can see that?
We can see, Yep,
Yes,
and it's not full screen yet, though.
Okay. No?
Well, we can still see your browser, if that's okay. Are you going to scroll down in the browser?
Mm-hmm.
Okay, yes.
All right. So my name is Alessio Russo. I'm the founder and the CEO of Robos. I founded Robos during 2015 with the goal to bring 3D printing, additive manufacturing to the production shop floor. So our goal was since the beginning to produce real end-use parts made in a repeatable way, close to the point of use. So our technology today is helping many aerospace companies to produce the parts they need just in time and on demand. A quick overview about 3D printing in the aerospace industry. Currently, the technology is mainly used to create prototypes, jigs, fixtures, molds for example, autoclave, hand layup composite, molding, tooling in general. But the technology now is getting ready to produce real end-use parts capable to fly more and more. So the expectations over the next 8 years is that the 3D printing sector will reach almost 7 billion business in the aerospace sector, including hardware, so 3D printers, materials, and parts printed through service providers. So the adoption of the technology in the aerospace sector is becoming huge year after year. In Robos, we are specialized in composite materials and superpolymers. So our technology is being developed to create end-use parts using superpolymers like PEEK and PEEK carbon fibers and ULTEM 9085 to replace metals in extreme applications. Here, for example, we are seeing an application of CubeSats printed with our technology by the University of Colorado. And thanks to the fact that they replace metals in these applications, especially aluminum, they had a cost saving around 88%, which is huge, and a mass reduction of around 50%. So, of course, PEEK material is one of the most performing polymer in the entire world. We introduced for the first time in the additive manufacturing sector for FDM technology, so fused deposition modeling, the PEEK material back in 2016. So we were the first in the world to make possible printing PEEK material, which is a very it's not a very easy to process material because it requires very high temperature to be processed in terms of extrusion temperature and in terms of the process, the temperature in the heated chamber. So we process this material at 450 C, so very close to the melting point of aluminum, for example. I'll be very fast because I understood that we are late. So a quick overview about our technology. As I was explaining before, we are very concentrated and focused in superpolymers and composite materials. Today, we demonstrated that the technology is now ready and it's now capable to replace metals, thanks to the fact that we reach incredible mechanical properties like 140 megapascal tensile strength. We certified material for aerospace use. So our materials are UL 94V0 certified, so flame retardant, smoke toxicity certification. And we are now ready to ensure the repeatability of the parts production thanks to our technology that we call beltless. So our 3D printers, as you can see, are more similar to CNC machine in the way our machines work. we can ensure 10 microns accuracy and repeatability over time, thanks to the fact that our 3D printers don't use belts made in rubber-like material, but they use mechatronic gears to create very accurate and repeatable parts. We introduced some business models in the last couple of years with the intention to democratize more and more our technology. So today we provide our machines and materials with a subscription fee. And thanks to this, we are creating a huge number of small manufacturing hubs in the world that we call robust 3D parts partners. These partners are our customers that provide parts service to additional customers. So we are creating the connection between the demand of printed parts and the offer of printing parts provided by our customers. We are capable today to produce up to 10,000 parts in the world in very few days, asking our clients to produce parts for us. At this point, we have more than 400 machines in 24 countries in the world, and we are we printed so far more than 50,000 of parts in the last 6 months. Here we can see a very short application we did in the aeronautics sector. This application is called hand-lay-up composite molding. So here we are helping aerospace companies to replace aluminum or generic metal molds with the PIC filled with carbon fibers. The very good thing is that this material printed through our technology can outstand more than 7 bars at up to 180 C in the autoclave for composite parts consolidation. So this is a very aerospace ready material for very extreme applications. At this point, we are more than 100 employees, and we have 2 headquarters. The US headquarters is based in Houston, where we have parts production capability and all our business operations. In Europe, in Italy, we have R&D, engineering, and material science and chemistry team. So we are very interested in getting in touch with people participating in these webinars. If you have any kind of questions, or would you like to test and understand the capabilities offered by our technology, we will be very pleased to get in touch with you and let you test and understand what's today is possible thanks to the additive manufacturing.
Thank you, Mr. Lorusso. Thank you very much. Your presentation shows how Italy stays up to speed with the latest technologies. Do you see? I have a question. Do you see your composite materials for additive manufacturing doing what conventional composites, see them progressing in aerospace applications as it happened to the conventional composites? And yes, I mean, yes or no? And what are your what do you think are the limitations to their implementation?
Thanks, Antonio, for the question. I think that we reached incredible performances. So today we are already replacing aluminum and stainless steel materials and some composite parts as well. So thanks to the fact that additive manufacturing can provide incredible geometry, it's very difficult to be replicated by traditional composite production methods or traditional CNC machining. We are seeing more and more adoption of 3D printing technology, especially for PEEK, carbon PEEK and composite materials through our aerospace customers. We started from toolings, molding, but we are now expanding into flying parts more and more. So now we are at the point where we are qualifying our technology as a production technology for flying parts with many aerospace companies. So I see a great adoption of the technology, and the next years will be a huge opportunity for the 3D printing technology.
Thank you very much.
My pleasure.
And we switch to the next. Actually, I want to say again to the, no, not again, for the first time to the audience, please do not log off at the end of this symposium, because there will be a questionnaire with a few questions that will by itself open up at the end of the last presentation. So it only takes a couple of minutes. So stay connected, and please answer the few questions of this questionnaire. Okay, so let's move to the next speaker, and his name is Mr. Salvatore De Nicola, and he is here representing Solvay Composite Materials Global Business Unit. He has more than 20 years of experience in the composite industry as a researcher, material and process engineer, project leader, and R&D manager. He holds a master in aeronautical engineering and an aircraft certification from Cranfield University in UK. He also has attended Bocconi School of Management and Wichita University in US. He will talk about composites for aerospace industry. Please, Mr. De Nicola.
Thank you very much, Antonio, and thank you also to Filitalia and to the Italian consulate for inviting me. It's a great pleasure to be with you today. Well, let's start about talking a few words on Solvay. Solvay was established in 1863 by M. Solvay, who is the inventor of the process for producing soda ash. He was literally obsessed by innovation. He was convinced that innovation and progress are beneficial to both business and society. And for this reason, he introduced in his company for the first time at the end of the 19th century, the social welfare, introducing paid vacations, social security. And starting from 1911, he organized the famous Solvay conferences by inviting the most important scientists of the time. And let me say that after more than 150 years, Solvay is still literally obsessed by innovation. And demonstration is that a few years ago, the Solar Impulse 2, relying on the Solvay technologies, completed for the first time a trip around the world without a single drop of fuel. Few numbers now. Solvay has more than 23,000 employees in 74 countries. Last year, the net sales were about 9 billion of euros. Solvay is a global leader in chemicals, in materials, and in providing, generally speaking, solutions to the industry, in particular to aerospace industry, mobility, electronic industries, and healthcare industries. However, even being a leader, the company remained really focused on people and on sustainability of our business, in particular on green solution to protect our planet. Well, in the title of the presentation, I said that composites are a newborn technology. Why newborn? Because if we look at the development timeline for metals, we can see that we have been using metals for 10,000 years now. And even the alloys that we use today in the aerospace industry, aluminum alloys or some type of steels, have been, however, developed more than 100 years ago. While for composites, the story started in the middle of last century with glass fibers, if we neglect the mud brick used in the prehistory. And in particular, for thermoplastics, you can see that PEEK and PPS and other thermoplastic polymers that are very important today in the aerospace industry were developed only about 40 years ago. So composite, we can say that are at their infancy, in particular as fiber reinforced plastics, but evolved very quickly, and evolved quickly as also did aviation. Today we live in a digital era dominated by electronics, by connections, smartphones, satellites, and probably we believe that this is the most exciting period for progress. But if we look at the story of aviation, we can see that between the first flights and the first supersonic flights, there are less than 50 years. And it's incredible today to think that just 3 years after the first flights of the Wright brothers, the Voisin brothers in France started with the first plant to manufacture aircraft. So we can say that composites and aviations have for sure in common the rapid developments. And in particular, the introduction of composite into the civil sector, into the aerostructure for civil sector, started in the 70s. And since then, in 45 years, the use of composite materials increased more than 30 times, with an annual growth rate in some cases higher than 10%. We can see that in the 70s, only few aircraft adopted composite materials, and on average, the percentage of composites in weight was less than 10%. During the 90s, the number of aircraft using composites increased dramatically, and also the percentage of usage of composites increased up to 30%. While in the last few years, we have some examples like as the Boeing 787 or the Airbus A350 that uses more than 50% of composites in weight. Well, which are the technologies that were able to enable the use of composites in the airframe, in the aerostructures? We can see here a direct correlations. Let's start for who is not very familiar with composite materials with the definition. Composite materials can be defined as a material having at least two different phases and an interface. In few words, we can say that a composite material is made by fiber and matrix. And in the 70s, several types of fiber were developed, like Kevlar, E-glass, standard modulus carbon fiber, boron fibers, while on the racing side, the chemistry of epoxies made a giant step allowing to introduce composites in the aircraft secondary structures like as radome or rudder, spoilers, flappers, other movable surfaces, both for commercial and military applications. During the 90s, another significant step ahead was made by the development of intermediate modulus carbon fiber and of epoxy using toughening technologies. Toughened epoxy and intermediate carbon fibers opened the door, together with the BMI resins for high temperature, to the use of composite materials for primary structures like as empennage or primary structures for defense application. In the same period, started also some automatic deposition techniques for aerospace, in particular automatic laying or automatic fiber placements. And coming to our days, the racing for liquid infusion and the development of vacuum bag technologies allow it to extend use of composite materials to very large structures, in particular to wing, to empennage, and for military applications, enabled the range of aircraft missions for these aircraft. And where we are today, in particular, we can identify three main technologies that are making the difference in the aerospace industries. One is the development of out-of-autoclave materials. Again, for who is not very familiar with composites, composite materials are normally laid up and then are consolidated in large autoclaves using high temperature, usually 180 degrees C, and high pressure up to 10 bars. Of course, this implied the high cost, high manufacturing cost, and some issues in manufacturing very large structures. Now we developed materials that are able to reach the same mechanical performance of classic composites, but without use of an autoclave. They can be cured in a standard oven, and this allows it to extend use of composite to very large structure. The second technology is liquid infusion. Liquid infusion allows to realize very complex parts, like as the one that we see in the example here. There are fan blades for engine applications, or very complex shapes like as the hinge fitting that we see in the picture. And the third one is particle toughening. I said before that toughened epoxy adds a huge importance in the development of composites for aerospace. The adoption of an innovative system to produce toughened resins and using in particular some microscopic particles is allowing to extend composites to some very thin structures, and this makes possible use of composite materials also on small aircraft. Normally, in some areas, fuselage of an aircraft can be less than 1 millimeter, and use of composite materials in so thin structures were not possible until a few years ago. While now, with these new resin systems, everything is more affordable and responsible. Well, what does the future hold? We believe that to grow further, composite must deliver more value, and in particular, to address the needs of the emerging markets, urban air mobility, autonomous vehicles, electrical vehicles, sustainable solution for mobility. And we know that this more value is within the industrialization. Composites are now entering the industrialization era, where in some extent we can say that the production system can be more important than the product itself, because a product that is not sustainable, that cannot be produced easily and respecting the increasing demands of the markets, will not be considered as competitive. And the answer, we believe, is in mainly 4 technologies. One is press forming, another one is bonding, third is function integration, and last, and we have just seen the very interesting presentation from Mr. Lorusso on additive manufacturing. Just a few more details on each of these technologies. On stamping, today, thanks to the new chemistry and new processes developed by Solvay, press forming is possible for both thermoplastic and thermoset composites. Press forming allows complex design and a very high manufacturing rate. We can introduce to aerospace, finally, something that so far has been only dedicated to automotive markets. The production of parts with a very high takt time, so parts produced in minutes instead of hours. This will make the difference for the new emerging market sectors, as I said before, like as urban air mobility, and also on very large aircraft, reducing the cost. The second interesting technologies we are looking at is bonding. Today, the aircraft, both the metallic aircraft and the composite aircraft, use rivets, use millions of rivets. And this means issues in terms of safety, in terms of weight, and in terms of manufacturing problems, because before installing the rivets, the parts must be drilled and then riveted. Bonding, so far, has never been considered as a structural alternative to rivets, because it allows only a sort of mechanical adhesion between the procured composites and the other ends. While today, thanks to the FusePly novel product developed recently, we can ensure a chemical link between the parts. So after the co-cure, the effect will be to have a monolithic part without any interface between the adhesive and the composite parts. And this, we are sure, will make the difference in terms of manufacturing of bonded parts. The third aspect of the innovative technologies is functionalization. Today, composites already provide added functions to the structure. The composite protects the aircraft from lightning strikes, protect composite from fire, protect composite from electromagnetic interferences. But in the future, this functionalization can definitely improve. One of the examples is to use composites as a sort of batteries for energy storage. More composites on an aircraft would mean in the future having more space for batteries, for example. And this opened the door to full electric aircraft or aircraft relying on electricity more than on classic fuel for services and engines. And the last one is additive manufacturing. I don't want to add more words on this. We really believe that this is the future in a wire. Starting from a simple wire today, we can manufacture very complex parts, and this is enabling the use of composite materials on items that so far have been only manufactured by metals. In definitive, we can see that composites are a young technology, but the contribution to aerospace was for sure very decisive, and this will remain the driver for the future. Composite developments will be still driven by advanced both in material science and in automation. So the composite materials can continue delivering an added value to aerospace and in general to our day-by-day life. But the attention to sustainability is increasing, and we believe that will play for sure a critical role, because the future must be sustainable. Thank you.
Thank you, Ingegnere. Thank you very much. And let me see. There is a question for you. What, in your opinion, are the next plastic materials in additive manufacturing? How do you see the evolution of this, of plastic materials in additive?
Well, one of the most exciting innovations we are working on is the use of materials having continuous fiber for additive manufacturing. Today, we use reinforced plastics for additive manufacturing, but with what we call long fiber, but that, as a matter of fact, are not comparable to the continuous fiber that are used in, let me say, legacy composite materials. But we are quite sure that in the near future, we will be able to realize composite parts by additive manufacturing with exactly the same properties of continuous fiber.
Okay, thank you very much. Your presentation was interesting because you shed some light on the role that the contribution that materials have in innovation in aerospace. So you touched on a different, instead of on the aircrafts themselves, you touched on the contribution of the materials, particularly composites and plastic materials. So thank you for that. And finally, we switch from companies to a university. So the next and final speaker is Professor Rosario Pecora from the University of Naples, and he will with him we will dive into the theory and analysis of aircraft structures. And so a few biographical notes about Professor Pecora. He has earned a master's degree in aeronautical engineering and a PhD in transport engineering. He's also assistant professor of aircraft structures stability, and lecturer of advanced aircraft structures at the University of Naples, Frederick II. He has worked on several aircraft, for several aircraft manufacturing companies such as ATR, Alenia, Aermacchi, Bombardier, Piaggio Aero Industries. And he also has worked for research centers as technical advisor. His research activity is mainly focused on aeroservo elasticity, structures dynamics, and smart structures. Again, with him, we will learn about how innovation in aerospace can be carried on through innovative designs. Please, Professor Pegor.
Thank you, Antonio, very much for your presentation. It's a pleasure for me to be here with all of you today. I'm starting to share my screen. Okay. Do you see my screen?
Yep, looks good.
Perfect. Let me use the laser pointer. Okay, so in this brief presentation, I will give you an overview of the activities that we have been carried out within the framework of the Clean Sky program, with reference to the design and validation of a novel technology, a morphing wing flap, specifically conceived for large civil aircraft application. After a few words on the research framework, I will drive you through the conceptual design phase of this technology, and then to the executive design and to the validation of the system. Finally, I will give some comments on the next steps of the research and on all the improvements we are already making on the technology we have already validated. Well, our adventure started nearly 10 years ago in the Clean Sky program. For those of you who are not aware of what Clean Sky is, well, the Clean Sky is the largest research program that has been launched by European Union to specifically address all the technologies for the greening of the next generation aircraft and of the next generation air transportation. The program is very, very large. There are a lot of partners involved in it, small and medium enterprises, big industries, academies and research centers, and there are a lot of technologies investigated. This complex research program is arranged in different IADPs, which stands for Integrated Advanced Demonstration Platform. This means that all what is studied in the Clean Sky is specifically focused on an integrated platform for validation. So we are not making any kind of academic or research exercise. We are doing something that has to bring innovation, real innovation in the aircraft segment. The IDP we're working for is the Green Regional Aircraft, EIDP, and this EIDP is basically identified with a real aircraft that has been conceived by Leonardo aircraft into different configuration, open rotor configuration and turboprop configuration. Turboprop is over here and the open rotor configuration is over here. Well, why we have two different configurations? Because this kind of configuration, the turboprop one, was supposed to be the one that has to be flown in the very next future. This one was the configuration that is supposed to be flown in the far future. So all the major technologies had to be investigated with this, with reference to this kind of configuration, while the most breakthrough technologies, like the morphing structures, had to be investigated according to this specific kind of platform. Each EIDP, and so also the GRA, is characterized by different domains, and each domain collects, the technology for that belongs to a specific thematic area. We have been working in the low noise configuration domain of the GRA EIDP. In the low noise configuration domain, there were the investigation of all the technologies that were aimed at reducing airframe noise, so noise pollution, and also to improve the efficiency, the aerodynamic efficiency of the aircraft, with the final goal of reducing the fuel burnt and consequently the air pollution. So we have been working in the Green Regional Aircraft IDP with reference to this kind of configuration, open rotor configuration, to improve the efficiency of the aircraft through novel technologies in the structural field, so through morphing adaptive structures. Okay, that being said, the first task that we received from the industrial partner, in this case Leonardo Aircraft, that was managing the IDP, was to make a proof of concept. Basically, we had to design, manufacture, and validate a morphing architecture that was enabling to modify the camber of a single flap element in compliance with target reference shape. Why this? The basic idea behind this kind of proof of concept was very simple in principle. The idea was to replace a classical double slot flap system that you can see here with a single slot flap system. When you do this kind of replacement, you have advantages in terms of complexity of the system, but you lose something in terms of aerodynamic efficiency in generating high lift for takeoff and landing, because you need much more camber, much more curvature for this kind of airfoil in order to reach the target of the high lift you need for your aircraft. So the idea was to replace this complex system with a simpler one, but characterized by morphing capabilities. So it could be deployed out of the wing and cambered. That means the shape of the flap could be changed by increasing the curvature of the airfoil itself. We worked as structural engineers in this task, and basically the way according to which we had to morph the structure, so change the shape of the structure, was given to us by other partners working in aerodynamic field. So basically they discovered what was the target morphed shape of the airfoil we had to reach with our morphing structure in order to enable, with this kind of configuration, the same high lift performance of the double slot system. As a constraint, this is very important to say, in the clean sky, we were obliged to not think about exotic solution, extravagant materials, stuff like that, because we had to stay with our foot on the ground and think about technologies that could be really implemented on a civil transportation aircraft in the next future. So technologies that could be ready for certification. So the idea that we had to find out a structural solution enabling the transition of the flap airfoil from a baseline unmorphed configuration here in red to a morphed one was to replace the classical rib structure, which is a unique piece, a unique plate, with a segmented structure characterized by multiple plates connected along the middle line of the airfoil through hinges, here represented with A, B, and C. Moreover, not consecutive elements of the ribs were connected to crossed links, here this segment, and in the opposite side this other segment. Thanks to this specific connection, basically we generated a single degrees of freedom system, in the sense that if you think of moving each of this segment, all the other follow the movement according to a specific gear ratio across these hinges that is depending by the position of these links. So you may think about this kind of rib as a finger, okay, as a finger of your hand. You cannot move the part of the finger of your hand in an independent way. You move one part of, unless you have problem, of course, in your hand. If you don't have any kind of problem, if you move just one part of your finger, okay, all the other parts follow the movement because you have nerves inside your finger that generate some specific gear ratio between the parts of the finger itself. So this rib follows this kind of concept. So it's a finger that has to that allows the change of the shape of the airfoil. And if we play with the position of this crossed links, the nerves of your finger, you can basically obtain this transformation from this configuration to this configuration. Well, how you obtain this transformation, of course, by introducing to your rib an actuators that move the ribs itself. Going into the 3D, okay, along the span, you see how the things worked in this proof of concept we elaborated. Basically, you recognize here the segmented rib, okay, the segmented rib, and here we have a portion of the flap in true scale limited span. And you see that we have the 3 ribs delimiting 2 bays and some stiffening elements along the spanner to ensure the adequate stiffness in withstanding external load. Closer to each rib, we have a rotary actuator. The rotary actuator basically generates a rotation of a shaft that is perpendicular to the rib plane. This rotation in this direction through a gearbox is switched into a rotation in a direction that has in the chordwise, okay? A direction that is in the chordwise direction. This rotation in chordwise direction is transferred to an endless screw that moves up and backbound and forward the cursor colligated to this, linked to this leverage that moves finally this block up and down. So basically this mechanical arrangement here allows the actuator, the rotor actuators, to move up and down this block. while doing this, the action of the actuators is amplified through all these leverages. So we do not need anyway very large actuators to move the flap under the action of the relevant loads that you have on this segment, because you have to consider that when you are designing a morphing structure, you are designing a structure that has a double functionality. The basic functionality, that is the one that it has to withstand load with adequate margin of safety. The second functionality, it has to do that while changing the shape, and that's to preserve the shape under the action of load itself. So these actuators are integral part of the structure in doing this reaction to the external loads. Of course, this conceptual layout was the result of a very long process, a very long design process, from the concept identification up to the advanced design and also the kinematic design. Finally, we made up the demonstration of this first concept. We manufactured a prototype, all in aluminum alloy, and we performed experimental tests on this small portion of the flap. Basically, we did static tests in order to see that the device was able to withstand external load with positive margin of safety, with no permanent deformation. And then we performed the ground vibration test to understand how the dynamic of this new kind of structure would have influenced the dynamic of the structure of the wing where this flap has to be installed on. And then we made functionality tests to prove that we were able actually to morph the shape according to the way that the aerodynamics told us to do. So you can see in this video how this structure that is segmented and is characterized by very conventional mechanical arrangement can actually change the shape in a very smooth way, okay? In a very smooth way and in compliance with what was required by the aerodynamicists in terms of final shape of the flap segment. Of course, we have here now the reverse of the transformation. After this proof of concept, the industrial partner we were working with, so Leonardo Acat, was very happy and satisfied. And so basically they increased a little bit our budget, and they asked us to play a more challenging task, So, okay, provided that you are able to demonstrate that you can morph a portion of the flap structure, let's now move to the investigation of a larger portion of the flap. So basically they gave us as investigation domain a wider portion of the flap, characterized by a span of 3.6 meters and tapered configuration with a root chord of 1.2 meters and a tip chord of 1.2 meters. So we had to tip chord of 0.9 meters. We had to, demonstrate that we were able to morph this kind of structure, but with reference to a wider domain, and with reference to another important requirement that we had to implement two different kind of morphing capabilities. So not just one morphing mode, as you saw before, that the airfoil changed the shape, but two morphing modes. What are these two morphing modes and why? The first morphing mode is the overall camber morphing of the airfoil, as you have seen before in the proof of concept. So basically you change all the curvature of the airfoil, all the camber of the airfoil, and you are supposed to implement this kind of morphing mode when the flap is deployed, so it's out of the wing. Why you do that? Because by cambering you increase the performance of the aircraft in generating high lift, and so you need in takeoff and landing a higher lift, and so you morph this part completely. When you are in cruise and the flap is stowed in the wing, just this portion of the flaps that comes out of the wing was required to move up and down in order to control somehow the load distribution on the wing and to have some advantage in terms of aerodynamic efficiency. So we had to assure two different kind of morphing modes that were also associated to different kind of zones of areas of the flap that had to be basically morphed. The first concept we elaborated to solve this problem, to solve this hard problem, was to somehow extend the degrees of freedom of the finger-like rib that we had that we have generated in the first phase of the project. And the most simple way to do that was to make that crossed links, the nerves of the finger-like rib, extendable. So you have always the same arrangement of the rib that I showed you before, but one of the link, this one, can be extended in length. Why this? Because if you extend this link in length, basically you can generate a torque around this hinge and you can move up and down the last portion of the flap as it was required. So with this arrangement, we have a double actuation for the rib. One actuator drives the classical leverage that we have seen before, and with this actuator stopped, and this means that this length is fixed, all the flaps change the overall camber. When this actuator stops, the flap is fixed in a shape. This actuator can be activated, and this activation, thanks to a particular gearbox, generates the extension and the contraction of this link, just moving this part only. We went through the overall 3D design also of this kind of architecture. This is how the architecture looked like also in this fancy rendering mounted on a real aircraft. And please consider that we have here for all the ribs involved in this layout, two actuators per rib, two rotary actuators per rib. This is just an extension of what we have seen in the first preliminary proof of concept. We solved the problem of the tapering, just tapering the trailing edge and leading edge of the flap while keeping a constant short here where all the mechanics is installed. In this way, we were able to preserve the fact that all the hinge lines of these ribs were orthogonal to the rib plane, thus avoiding a lot of complication and problems of jamming during the morphing. While we performed all our investigation, we came out with the executive layout that finally was rejected by ourselves because was not complying with a very important requirement. We had to keep in mind that we were developing new technologies for civil aviation. Okay, so we can do morphing, we can change the shape of the flap, but we have to think about the fact that it has to be convenient, not only for the impact on aerodynamics, but also for the impact on maintenance and installation and all other issues. So this kind of architecture was too complex, to be proposed for real industrial implementation because it had many actuators, many pieces. So we wanted to simplify it a lot. And we finally found out this revolutionary layout for the rib, much more compact than the one that you have seen before. The rib is always actuated by two different rotary actuators, but this time the actuators are not just dedicated to one rib only, but to the two ribs that are delimiting each bay of the flap. Moreover, the mechanics was really improved. As you can see here, we have a finger-like structure for the first three elements. So these first three elements are mechanically linked and connected. So this means that if we move just one of these three elements with respect to the other, all the three elements moves as a single degree of freedom system. This actuator basically was dedicated to the motion, to the cumbering of these three elements that you see here, while this one was dedicated only to the flap tabs, to the last segment. So when we had to implement the overall camber morphing, both the actuators had to move, and they had to move in a synchronous way in order to reach the shape we wanted for aerodynamic reason. When the flap was stowed in the wing, this actuator was stopped, and just this actuation was functioning, just moving up and down the flap tab for load control functionalities. All these mechanics that you see here inside were just internal leverages in order to amplify the action of the actuators, because one of the important requirements in the clean sky is that we had to use electric actuation. We had to go in the direction of all the electric aircraft. When you use electric actuation, you do not have so much torque at your disposal, so you have to figure out somehow how to amplify it through some mechanical leverages and mechanical amplification. This is the layout, how it appears after all the optimization study we did. Basically, you see, we have a couple of actuations for per bay, not per rib. So we reduce a lot the number of actuators needed. Moreover, not all the bays are actuated. Here we installed the controller for the segment. Of course, this is was just something that we did for because it was much more comfortable for us for demonstration purpose to have everything inside the demonstrator. But of course, for real aircraft application, this controller must be placed into the fuselage. And all these actuators worked in a synchronous way with the specific control logic we implemented. Basically, we have a primary line of actuators and a secondary line of actuators. This line moves when we had to move just this last portion of the flap. And this one, together with this one, moves all together to morph the entire camber of the flap itself. The entire set of actuators is linked to the rib here through some harmonic drive gear reducer, which amplify a lot the torque coming from the actuation by 120 times. So we have small energy required and high torque provided. Moreover, we have another amplification inside the rib itself that further amplified by 13 times the torque coming out from the harmonic drive gear reducer. As you can see here, there is a missing element in the structure. I didn't show it intentionally, is the skin. When you design a morphing structure, you have to think about a skin that is able to accommodate the change of shape. And you have basically two kinds of ways to think about your skin. You can think about a stretchable skin, so a skin that is very elastic, that can be stretched and compressed. And you can think about a segmented skin, okay, like in this other layout, that is composed by different segments that can slide on each other. The first one is much more performing from the dynamic standpoint. The second one is much more performing from the maintenance standpoint, from the construction standpoint, from the robustness standpoint, and for a lot of other things. We were very lucky because during that period where we were designing for the Clean Sky, we have been involved as design leaders for the morphing trailing edge in Saristu project, led by Airbus, and in another project where we were leader for the design of a morphing aileron for Bombardier regional aircraft. In both this project, we were dealing with the design and manufacturing of the morphing devices, and we also had the opportunity of test them into the wind tunnel. Well, what we discovered is that even if you have small gaps with a segmented skin, you do not have a great influence on the dynamic standpoint because of the position of your trailing edge, in our case of the flap. The flow is not so clean in that area, so you are more keen to accept some aerodynamic some lower aerodynamic performance due to the gap, because you want to gain advantages in terms of production and also maintenance of your final layout. So for the flap, it was considered not reasonable to go on this kind of solution, very smooth solution, because it was proved that no advantages, relevant advantages from the running standpoint could have been achieved. And so we implemented the armadillo-like skin for the architecture I showed you before. Basically, we have different segments sliding on each other. Here, it's the structure that is represented the structure, skin and structure in overall camber morphing mode, and here in the secondary morphing mode, where just the top is moved, downwards and upwards for load control capabilities. A zoom of the skin has just to show you how it was conceived. You have here silicone seals in order to avoid the flow leakage around the panels, so to anyway assure a very, very smooth aerodynamic flow.
Hey, just to cut in briefly, we're coming close to the time.
Yeah, I'm finished.
You're finished? Oh,
yes, just a couple of videos to see at the end of the game how it works.
Great.
Yeah.
Okay. Thank you.
So it was just not an exercise. We actually made a static test on this device up to the limit load that was 1.5 tons, and the structure well resisted, remaining in the elastic field. and here is the unloading. Consider that this shape is also kept by the actuation itself. And here you have, a video in order to show you how the structure actually morphs. Okay, this is the overall morphing mode of the system. Morphing mode 1, and here we have the tail of the actuation, and morphing mode 2, just this part is moving. Some details of the transmission line with a very sophisticated solution to avoid undetected failures. And here you have the secondary morphing mode that is supposed to occur when the flap is stowed in the wing. Okay, as next steps, okay, just a few words. We are now in the Clean Sky 2 program. We are dealing with true scale, also in the span length flap design and manufacturing. And this time we assure 3 different morphing modes, the 2 that you have already seen, plus a twist of the top. We are now in the executive design phase. We are supposed to do the wind tunnel testing by the end of this year, and next year we will have the ground validation of the full demonstrator, full size demonstrator. So let's hope that we will be successful also with that challenge. So thank you for your attention, and greetings from Napoli. Saluti da Napoli.
Thank you, Professor Pecora. I know we're short on time, but it was fascinating presentation because you let us take a peek in the near future of airplane structures, and also a peek inside the airplane wings, right? We only see the skin, we don't see the inside. So I'm not sure we feel safer or less safe now flying. Anyway, so I have a question for you. Let me see if we can do it. If you have a quick answer. Is the weight of the morphing flap greater than the weight of a conventional flap?
Yeah. Well, yeah, this is a classical question. The weight is, of course, greater because you are dealing with a structure that does something more. So you have some equipment installed on it. But what is important to say is that what you pay in terms of weight is gained in terms of efficiency that you obtain at the aerodynamic level. So the balance is positive at the end of the game.
Okay. Thank you, Professor. And I'm closing this this event. Many thanks again to our esteemed speakers and their organizations. Thanks to the Italian Consulate and Filitalia International. Thanks to Hyper Design, and many thanks to those who attended our event today. We hope that you will be back in 1 month for a symposium on additive manufacturing or 3D printing. Ringrazio coloro che hanno assistito a questo evento e do a loro l'arrivederci tra un mese per un altro evento che riguarderà la stampa a 3 dimensioni o additive manufacturing. And finally, a last reminder about the survey that will automatically open up when you leave this event. Again, thank you very much to everybody, especially the speakers. They made this event very interesting. And I will see you, the audience, in about 1 month.
Antonio, posso dire qualcosa?
Prego, prego.
Sì, complimenti, veramente complimenti. Compliments to all of you. I just wanted to let you know that we have a program of expansion. If you know anybody, any leaders who is interested in starting a chapter in any location, let us know. We're going to Latin America soon. And è stato un piacere ascoltare tutti voi. Professore Rosario Pecora, abbiamo 2 chapter in Campania, una a Salerno con la bravissima professoressa Sara Carbone e una a Napoli con Michela Mortella. Arrivederci, io sono calabrese, ciao.
Arrivederci, piacere.
Arrivederci, ciao. Goodbye, to the next time. Ciao, ciao.
Bye bye.
Grazie Antonio.
Grazie.
Prego, prego.
Okay, closing